Hello everyone, welcome to the course titled Optimization Methods for Energy Systems. Today we begin with mixed integer programming. This branch of mathematical optimization combines both integer and continuous variables in the decision-making process. That's why we call it a mixed integer programming. Um, we have a main question here: why do we need mixed integer programs? The answer lies in the nature of variables that influence our decisions. And not all variables in real-world optimization problems can take fractional values. As a general example, we can mention shift scheduling, where we decide how many shifts each employee should work. As a rational decision, we cannot assign, for example, 3.6 shifts to an employee. That's where integer variables come in. A more technical example is distribution network expansion planning. In this case, the operator of the network must answer different main questions: when, where, how many, and what type of equipment must be added to the current configuration of the network to satisfy a set of techno-economic and environmental objectives under a set of limitations. The answers to all these questions will appear in the form of integer variables. As we can see the left diagram on the screen, this diagram uh, represents the baseline distribution network configuration, and the right diagram, this diagram, illustrates the final network topology at the end of the planning horizon. As we can see, there is a different configuration at the end of the planning horizon in comparison to the initial configuration of the distribution network. Okay, here we discuss the branch and bound method, a widely used algorithm for solving mixed integer programming problems. The basic idea is to divide the optimization problem into a smaller subproblems and solve a relaxed version, discard or split path that cannot contain the optimal solutions. I think it can be a good idea to discuss the branch and bound method using a simple general example. Then we will solve different mixed integer programming optimization problems in the field of power and energy system studies. Okay, we have a general example here. A machine shop wants to purchase presses and lathes. Each press increases profit by $100 per day, while each lathe increases the profit by $150 per day. There are limits on both the budget and floor space. The required floor space and the purchase price for each equipment are given in the table, as we can see from this table. The key question is how many of each machine should be purchased to maximize the daily profit without exceeding constraints. Uh, Before solving, we need to formulate the optimization problem mathematically. Uh, That means identifying the decision-making variables. We have two decision-making variables: x1 number of purses and x2 number of lathes here. Also objective function. The objective function is to maximize daily profit: 100 x1 plus 150 x2. And also we have different constraints in the problem. We have a budget constraint. 8,000 x1 plus 4,000 x2 must be lower than or equal to 40,000, as we can see from here. And also we have a space constraint, 15x1 plus 30x2 must be lower than or equal to 200, this constraint. And non-negativity and non-negativity constraint. It means that x1 and x2 must be greater than or equal to 0. And also we have another constraint here, as we can see. x1 and x2 must be integer. So we have a full mixed integer linear programming, as we can see on the right side of this slide. We have the whole structure of the mixed integer linear programming form of the optimization problem here. The branch and bound method begins by solving the problem as a linear programming or LP model by relaxing the integer requirements. It means that we have to allow x1 and x2 to be continuous. This process gives us a starting point that's easier to solve using linear programming tools. In the first step of the branch and bound method, we must solve the relaxed LP or linear programming form of the optimization problem. So we ignore integer nature of the decision making variables in constraints and transform the mixed integer programming optimization problem into a linear programming optimization problem. This slide describes the LP form of the optimization problem. We can use different techniques such as the simplex method that we discussed in the previous sessions to solve the LP form of the optimization problem. Solving the LP form of the optimization problem gives us the optimal solution. As we can see from here, the optimal solution in the optimal solution, x1 is 2.22, x2 is 5.56, and the optimal objective value is 1055.56. This solution gives the upper bound of the objective function even if it's not an integer. However, since these values for the decision-making variables are non-integer, further branching is needed. So we use a tree diagram to manage branching decisions in the branch and bound methods. After solving the LP form of the optimization problem, we must define bounds. As I said, the upper bound is our relaxed solution, or 1055.56, this solution. The lower bound is calculated by rounding down the fractional values. This process gives us a feasible integer solution with a profit of 950. But this solution is not necessarily optimal. It means that to calculate the lower bound, we ignore the fractional part of the decision-making variables that we obtained from the relaxed LP model or LP form. We ignore the fractional part and solve the problem for these values, for x1 2 and x2 5. And the objective function value in this case is 950, and it's the lower bound. As I said, to calculate the lower bound, we round down x1 to 2 and x2 to 5. and the objective function value or the daily profit for these values of the decision making variables is 950. Uh, Having the upper bound that we obtained from the relaxed LP form and the lower bound that we obtained from the rounded down integer solution of the optimization problem, the real optimal integer solution must lie somewhere in between. The next step is to split the LP relaxed form into two new subproblems or branches. An important question arises here: from which decision making variable should we create branches? The answer is from the decision-making variable with the largest fractional part. As we can see from this slide, x2 has a larger fractional part. Therefore, the x2 has we select x2 to create branches. Now we split the optimization problem into two new branches, one enforcing x2 be lower than or equal to 5 and the other enforcing x2 be greater than or equal to 6. Let's explore the first branch or node 2, this node. Uh, In node 2, we constraint x2 be lower than or equal to 5. Here we have to add this new constraint to the relaxed LP form of the optimization problem. This process creates a new relaxed LP form for the optimization problem, as we can see from the left side the slide. This LP form of the optimization problem, and this new constraint are added to the problem uh, are added to the new problem. Solving the relaxed LP form again gives an optimal solution, and in this solution x1 is 2.5 and x2 is 5 with a profit of 1000. This value is an improvement over our previous lower bound of 950, but it's still not fully integer, so we will keep exploring. We move to node 3 with the constraint x2 x2 must be greater than or equal to 6. Again, we have to add this new constraint in node 3 to the relaxed LP form of the optimization problem. This process creates another relaxed LP form of the optimization problem, and solving the relaxed LP form gives an optimal solution. And in this optimal solution, x1 is 1.33, x2 is 6 with a profit of 1033.33. Both solutions obtained in node 2 and node 3 have fractional parts, but it's another piece in the puzzle. And as we go deeper, we get closer to the optimal integer solution. This slide visually illustrates the feasible solution space for node 2 and node 3. Each region is shaped by intersection of all constraints, including the branching ones. Consider node 2 in the graph on the left side of the slide, this graph. We can see the effect of adding constraint x2 lower than or equal to 5 to the feasible region of the relaxed LP form of the optimization problem. In the same way, for node 3, in the graph on the right side of the slide, this graph, we can see the effect of adding constraint x2 greater than or equal to 6 to the feasible region of the relaxed LP form of the optimization problem. The feasible regions clearly show the intersection of all constraints and how each node affects the potential solution space. We can see how the optimal values lie within those shaded area. Uh, it should be noted that black dots show relaxed LP solutions. They are not feasible in mixed integer programming yet, but they guide the search. These the black dots and this tree. This slide compares the bounds and the results from both brands. For node 2, the lower bound is 950 and the upper bound is 1000. For node 3, as we can see from here, the lower bound is 950 and the upper bound is 1033. We must continue splitting nodes until we find the optimal integer solution. This step-by-step branching ensures that we don't miss better solutions. But another key question arises here. From which node should we continue? Node 2 or node 3? The answer is that we should continue from node 3 because its upper bound is higher than the upper bound of node 2. Since this is a maximization form of the optimization problem, we always select the node with the highest upper bound, as it offers the greatest potential for finding better solutions. Here, node 3 represents the most promising branch in our search for the optimal solution. The next step is split the LP relaxed form of the optimization problem at node 3 into two new subproblems or branches. From which decision-making variable should we create branches? The answer is from the decision-making variable with largest fractional part. In node 3, the optimal solution is x1 1.33 and x2 is 6. Since only x1 has a fractional part, we select x1 to create branches. We split the optimization problem into two new branches, one enforcing x1 lower than or equal to 1 and another enforcing x1 greater than or equal to 2. Let's start with node 4, where we constrain x1 lower than or equal to 1. Here we must add this new constraint in node 4 to the relaxed LP form for the LP form of the optimization problem. In other words, we must add new constraints of node 4 and also node 3 to the initial relaxed LP form of the optimization problem. It means that we must sweep and consider all branches and their constraints from the first node, from here, toward the relevant node that we are working on to here. On the left side of the slide, we have the relaxed LP form of the optimization problem at node 4. And as we can see, we have two new constraints in this problem that are related to the node 3 and node 4. Solving the relaxed LP form again gives an optimal solution. In this solution, x1 is 1 and x2 is 6.17 with a profit of 1025. At node 4, we have an integer value for x1, but since x2 is still non-integer, further branching is needed. After exploring node 4 with the constraint x1 lower than or equal to 1, we now branch in the other direction, node 5. In this node, we constrain x1 be greater than or equal to 2, this constraint. Here we must add the new constraint in node 5 to the relax LP form of the optimization problem that we have at node 3. This process creates new relax LP form for the optimization problem, as we can see from the left side of the slide. Or in other words, we must sweep and consider all constraints from the first node to the last node that we are working on in this direction. And as we can see, we have this constraint and also this constraint uh, in the LP form of the optimization problem. These two constraints. We solve this relaxed linear program. However, as we can see from the bottom of the slide, the solution is infeasible. It means that no point satisfies all constraints simultaneously. This means the node 5 does not yield an feasible integer solution. So we discard this node in the branch and bound tree. This slide illustrates the updated branch and bound tree with added bounds for node 4 and node 5. Node 4 has an upper bound of 1025.50 and the solution is x1 1, x2 6.17. Node 5 is marked as infeasible, so its upper bound is infinity. Even though node 4 has a feasible solution, x2 is still not an integer, so we must branch again. The next step is to split the LP relaxed form of the optimization problem at node 4 into two new subproblem or branches. As we know, we have to create branches from the decision-making variable with the largest fractional part. In node 4, the optimal solution is 1 and 6.17 for x2. Since only x2 has a fractional part, we select x2 to create branches, as we can see from here. To eliminate the fractional value of x2 at node 4, we branch again by defining two additional limitations. x2 must be lower than or equal to 6 and x2 must be greater than or equal to 7. Let's start with node 6, where we constrain x2 lower than or equal to 6. Here we must add the new constraint for node 6 from node 6 to the relax LP form of the optimization problem that we have at node 4. This process creates a new relax LP form for the optimization problem. In the other words, we must add new constraints from nodes 3, 4, and 6 to the initial relaxed LP form of the optimization problem. It means that we must sweep and consider all branches and their constraints from the first node toward the relevant nodes that we are working on in this direction. And as we can see, we have this constraint, and this constraint in the LP form of the optimization problem. In this side of the slide here, we have the relaxed LP form of the optimization problem at node 6. As we can see from this problem, we have three additional constraints that are relevant to nodes 3, 4, and 6. Solving this relaxed LP form gives an optimal solution. In this solution, x1 is 1, x2 is 6, with a profit of 1000. Both, as we can see from this solution, both values are now integer, and this is a candidate integer solution for the optimization problem. After exploring node 6 with constraint x2 lower than or equal to 6, we now branch in the other direction, node 7. In this node, we have another constraint: x2 must be greater than or equal to 7. Here we must add the new constraint in node 7 to the relaxed LP form of the optimization problem that we have at node 4. This process creates a new relaxed LP form for the optimization problem, as we can see from the left side of the slide. Uh, It means that we must consider all constraints from the first node to the last node that we are working on in this direction. We have this constraint, and this constraint. We solve this relaxed LP form of the optimization problem. However, as we can see from the bottom of the slide, this node becomes infeasible. It means that no feasible region exists for the set of constraints. It means that we cannot find a solution that satisfies all constraints simultaneously. And it means node 7 does not provide an a feasible integer solution. So node 7 is discarded. This diagram illustrates the fully updated tree. Node 6 is the best feasible integer solution found so far. In this solution, x1 is 1, x2 is 6, with a profit of 1000. All other branches either had fractional values or were infeasible. Therefore, this is our final solution. We now interpret the optimal solution in the context of the original optimization problem. If the machine shop owner purchases one press and six lathes, then the daily profit increases by $1,000. And this slide outlines the general steps of the branch and bound method for maximization problems. In the first step, we must solve the LP relaxation form of the optimization problem by ignoring integer constraints. In step 2, we must store the answer as an upper bound. In the next step 3, we have to choose the most fractional variable to branch. In step 4, we must create two new nodes, one floor, one ceiling of the fractional value. And in step 5, we have to add new constraints to the optimization problem. And in the next step 6, we have to solve the relaxed LP form again. In step 7, if an integer solution is found, compare it with the current best. And in the last step 8, we have to repeat until all branches are exhausted. Please keep in mind that in the optimization problems with a minimization form, the direction of bounds reverses. It means that the upper bound comes from integer solution, and the lower bound comes from the LP relaxation. This slide presents a new exercise to solve using branch and bound. You can solve this optimization problem using the steps of the branch and bound method. Identify where to branch, which bound apply, and find the optimal integer solution. Thank you so much for your attention.